So here we have a couple problems related to angular momentum. Okay, and the first one I think is really interesting. We're asked to calculate the angular momentum of the Earth due to its orbit around the Sun. Right? Because the Earth is rotating around the Sun, it's traveling in a circle or approximately a circle around the Sun. It has some angular momentum due to that motion. And then we want to compare that to the angular momentum of the Earth because it's spinning, right? It's rotating on its own axis. Okay, so let's do the orbit around the Sun first. So we can draw this sort of thing. So there's the Sun, here's the Earth, clearly not to scale. And we travel around in something resembling a circle. We're going to model it as a circle. It obviously is not, but this would be a good order of magnitude estimation. So we're looking for angular momentum. Remember that angular momentum is an L, and it's defined for a rotating object as the moment of inertia times the angular velocity. Okay, so we're finding the angular momentum due to orbit, so I'm going to call this L sub O. Okay, so then we need the moment of inertia for the Earth as it's rotating around the Sun, and the angular velocity of the Earth as it's orbiting the Sun. So the Earth is small compared to our distance to the Sun, so I'm going to treat it as a point mass in this case. So if you remember, a point mass is simply mr squared. So this is mass of the Earth times this r squared. And omega is the angle that we sweep per second, right? Like how many radians per second do we travel around the Sun? So what we do know, or what you can pull out of your head, is that we complete one rotation in a year, right? That's actually an omega value, right? Rotations per year. It's a fraction of a rotation. It's a whole rotation actually per unit time. Then we just need to convert this. Okay, so we can plug in some numbers. These are not numbers that I know off the top of my head, but this is what Google was invented for, right? Is figuring out this sort of thing. So if you Google this, you can find that the mass of the Earth is 5.97 times 10 to the 24 kilograms, and the radius of Earth's orbit, or the average radius, because again it's an ellipse, it's not really a circle, but the average orbit is 149.6 million kilometers. So I want to do this in SI units, so I'm going to convert the million, that's a 10 to the 6, and kilometers as a 10 to the 3. That puts us in meters. Okay, so that's all I, right, the moment of inertia. And I also need to multiply by omega. So one rotation is 2 pi radians. I'm going to put 2 pi up here. And 1 year is 3,155,6,926 seconds. Okay, so if you do this math, if you multiply this all out, what you get is 2.66 times 10 to the 40 kilogram meters squared per second. Okay, so this is the angular momentum of the Earth as it orbits the Sun. Right? That's a huge number compared to the things that we've calculated, like lab scale objects. But we expect it to be huge because we're talking about the Earth. Alright, so let's compare that to the Earth rotating on its own axis, or spinning on its own axis. So we can Draw it right here. So this is the Earth. Okay, and maybe that's the axis of rotation, and we're rotating around this, and we have some radius r. So we're modeling it as a sphere. Again, the Earth isn't exactly spherical, but we'll model it that way. So we'll call this L sub s for spin. Right, so the Earth is spinning, so we'll call it spin. Equals I times omega again. Okay, but it's a different I and a different omega. Right? We're treating the Earth as a solid sphere, so we'll call this 2/3 m of the Earth times radius of the Earth squared, so we can say RE squared. Again, that's a different number than before. Times omega, so we rotate once per day, so it's a different omega. Okay, so now we can plug some numbers into this. The mass of the Earth is actually the same as what we had before. It was 5.97 times 10 to the 24. The average radius of the Earth is 6,378 kilometers, so that's times 10 to the 3 squared to make it a moment of inertia. And then omega, this is 2 pi rotations in 86,400 seconds. So if you multiply this all out, what you get is 1.18 times 10 to the 34 kilogram meter squared per second. Alright, so you can see the moment of inertia due to the orbit is quite a bit bigger, right? In fact, if we say, let's do the ratio, just so we can see how much bigger. If you divide these two numbers, you get that the angular momentum due to orbit is roughly 2 million times bigger than the angular momentum due to our spin. Alright, but what's more interesting than this number to me is the fact that the Earth has 2 types of angular momentum, or angular momentum from 2 sources. Alright, one due to this orbit, the circular motion, and another due to spinning. In fact, what's really interesting is that when you look at atoms, electrons orbit, or can be considered to orbit nuclei in this way. So they have an angular momentum due to this motion. They also have something that we call spin that you can imagine in this way. So it's really interesting that things on the grandest scale have a mirror image in things on a very small scale. That's just part of the beauty of physics. Okay, so moving to the next problem. We have a solid disk that's initially rotating at some angular speed. A second disk is dropped onto that disk, and the two spin together at some final rotational speed. The question is, when you do this, what is the final rotational speed? So this is actually a rotational collision problem, right? Very similar to collision of two bodies in linear momentum. It's just these things are rotating instead of moving in a linear fashion. So we're going to use the same idea we did for linear collisions, is that the momentum is conserved. So L initial equals L final. Alright, so this is the total initial angular momentum. It equals the total final angular momentum. So beforehand, maybe we can write I A times omega A initial plus I B omega B initial. And I'm going to recognize right off the bat that these things rotate together in the end, so I'm going to write this as IA plus IB times omega final for the right-hand side of this equation. So I can take one step that simplifies this. The disk A is not rotating, so omega A is 0, so that term cancels out, which is super convenient. So now maybe I can substitute some expressions for these. So IB, this is a solid spinning disk, right? And if you look at the equation sheet for that, you get 1/2 mr squared as the moment of inertia for that, times omega initial equals IA plus IB, and we're told that these are identical disks, so that's actually 1/2 mr squared plus 1/2 mr squared times omega final. Okay, so I'll do one more step and then maybe take a simplification here. So I can plug some numbers in. You'll see in a second that I actually don't have to. But I'll go ahead and plug some in. So the mass of this is 0.25 kilograms. The radius is 5 centimeters. They give us the diameter, so we need to be careful about that. The diameter divided by 2 is 5, and then converted to meter is 0.05 meters squared times omega initial equals, so these two terms are the same, so I'm going to pull out 2 of 1/2 times 0.25 times 0.05 squared times omega final. Alright, but I can divide this entire term and this entire term, so I'm dividing those on either side, and what I simplify this to in this case is omega final is 1/2 omega initial over 2, which is 70 radians per second over 2, or 35 radians per second. So you see in this problem, I didn't even need to know anything about these disks other than the fact that they are identical. So you don't always have that, that's not always the case, but because they were identical in this case, the algebra gave us simply this factor of 2.